Hello, everybody. It's a good Tuesday out here in Tucson. As I was mentioning before a few people came, it's going to be 94 degrees here today, which is actually 6 degrees cooler than yesterday. I just had we just had a conference out in Las Vegas where I actually felt cooler there than I do here in my new hometown of Tucson. So what I'm going to talk to you today about is predictive modeling using Monte Carlo method and simulative analytics. Now, when I put this together originally, I thought to myself, I can teach everybody how to use Monte Carlo method and how to put everything together. And I've done a few sessions on that before, and I actually even have a class in that available on our website for a small amount. But I realized that Monte Carlo method is kind of like a tool that has a very specific use, as all simulative analytics do. And you really can't. The real importance of Monte Carlo method isn't so much in its application, especially if you have a software package like, or analytics package like MATLAB or Minitab or IBM Model or even SPSS, all of which have Monte Carlo techniques as a feature of their package. And so really the actual use of Monte Carlo is not so difficult. I think, however, understanding what it's used for, why it's used, and when you want to use it is actually more important than the idea of just telling you exactly how Monte Carlo works and how to kind of program it into whatever software package you have. So let me now go over to the screen now.
I am. Okay. Oh, did you want it? I was going to borrow it if it was available. I'm sorry. No, it's not your fault. I was
Okay.
I know.
So,
Sorry, Greg.
By the way,
sorry.
if any
Let
of
me
you
interrupt
are,
for just a second. Let me interrupt for. Can you everybody mute, please? I'm having trouble hearing Greg over the conversations you're having in your office. Thank you.
Thanks, everyone. I just that's nice. Ask that myself. So many of the problems we have in fundraising ask us to predict future behavior of our constituents. We might be asked, for example, how many alumni will attend an event. Obviously, if we want to talk to the caterers or whoever we need to talk to before the event, we might need to give them a guesstimate of how many people are going to attend. We might also be asked how much money can we be expected to raise in a year from development officer asks. At many places I've worked at in the past, development officers were asked how much money they expected to raise from their asks during the year. And using Monte Carlo method, I was able to predict that for many of my development officers. And lastly, how likely it is that we'll reach our campaign goal. Now, obviously, this is falls more into the concept of campaign feasibility studies, and there are a lot of variables to put into identifying a campaign goal and the possibility of reaching it. But simulative analytics like Monte Carlo can give us an idea of the likelihood of reaching that goal. So Monte Carlo method in particular is really one of the most simplistic of simulative analytics. There are some models that are even more complex. Some of those are used by, for example, meteorologists or corporate data analysts who are trying to identify how many people are going to buy certain products during certain times of the year. The Monte Carlo method was named after this very imposing looking hotel and casino in Monte Carlo in Monaco. It was actually named, and you'll meet the inventor of the Monte Carlo method later in this presentation. It was named after the inventor because his uncle lost a lot of money here at the Monte Carlo casino. So what in general is simulative analytics? Really, it's a way to identify the likelihood of a certain number of events, each of which have a different probability of occurring or not occurring. And I know that sounds pretty vague. It's intended to be vague because there are a lot of different applications to simulative analytics. How many people will attend the event? How many people will make a gift? But how exactly do we do that? What do we need to know before we can start populating our analytics? So these are some of the things that simulative analytics can answer. I mentioned corporate sales. I know Target was a big innovator with simulative analytics. Then, of course, Amazon, which has dominated data analytics in the corporate world for many years now, got involved in simulative analytics, and really they're the market leaders now. Although places like Netflix are pretty good at trying to identify what you might want to watch next, and that's another application of simulative analytics. If any of you have AccuWeather on your phone, one of the neat things about AccuWeather, gives you a percentage likelihood that you're going to receive certain amounts of snow or rain over the next 24 hours. And that is also done through the Monte Carlo method. Although there are other simulative analytics packages that AccuWeather uses. Just as a kind of aside, my father actually knows the founder, was college friends with the founder of AccuWeather. So one of these days, I'd like to kind of use that connection to talk to them a little bit about simulative analytics. And another real world application, which came up kind of last week, is a craps player who changes their bets often. Is that going to do better than the guy that keeps betting on 9 all the time? And as Marianne will attest, I am the guy who just keeps betting on 9 all the time. In fact, this is a little illustration of my strategy in craps. I don't really know a lot about craps, so I just kept betting on 9, and originally did pretty well, not so well later. So you might be thinking, okay, well, you're talking about simulative analytics and using a predictive feature, but don't we have already something called predictive analytics to predict what's going to happen with, say, giving or donor behavior, or what might interest donors? And yes, that's true. And technically, simulative analytics is a subset of predictive analytics. The main difference really is how this analysis is performed and what kinds of predictive analytics targets need a simulation to resolve. Really, there are positives and drawbacks of simulative analytics. And because there are some drawbacks, we have to say that some predictions do not need simulative analysis. For example, let's say we're going to flip a coin 100 times. What's the likelihood if we flip a coin 100 times that we're going to see tails come up exactly 50 times? Now, technically, we could ask a computer to simulate flipping a coin 100 times and then run that simulation, say, 10,000 times, so that we identify the number of times within that 10,000 that we got exactly 50, divide that by 10,000, and we have the percentage possibility that the coin flips of the 100 coin flips will come up head, the heads will kill exactly 50 times. But obviously, there might be some statistical noise in that. It's not an exact replication of coin flips. There's always some randomness involved. Of course, if we run enough iterations of the 100 times, we're going to get very close to the exact answer, but never the exact answer that we could get if we could write a predictive equation to simulate these flips. In this case, we have a simple enough problem that we can write that equation because every coin flip has an equal probability of happening, and every coin flip contributes an equal amount to the number of heads or tails. So there's no coin flip that gives us 2 heads or 2 tails when we make the flip. Each flip is equal weight of each other. However, a lot of problems don't have the capability of being reduced to a single equation. We may have several events within each problem that have different percentage likelihoods, or we might have several of these events having a different weight within the problem. Some examples of this might be electoral college results, and this is actually another another reason I got into Monte Carlo is that Nate Silver at 538.com does his prediction of what's the likelihood not only that a candidate is going to win the electoral college, but also by how many electoral votes. That's done through a 10,000 example Monte Carlo simulation. He has a percentage probability of each candidate winning each state, and then since each state has a different weight within the electoral college, so Arizona has 10 electoral college votes, somewhere like Wyoming might only have 3, and then California has 55. There's no way to write a single equation that's going to emulate an iteration of the electoral college results. The same is true with something like weather forecasting. Each weather measurement has, like temperature and airspeed, has a different effect on future weather, and these effects are not easy to. They're not linear. What airspeed of 0 has a certain effect on weather. An airspeed of 5 miles an hour might have a certain effect, but then an airspeed of 10 miles an hour doesn't necessarily have twice the effect of 5. It might have some other effect that's nonlinear. Same with something like temperature or humidity. And each of those measurements has an effect on what location's future weather is going to look like. And because these are so complex, we are unable to write an equation to emulate them. We need to run a simulation and then try to identify, how many times a certain event comes up, or what's the mean or median. And when we do this, we're looking for, first of all, the measures I just mentioned, right? When my notes are one slide behind. But the first thing we're looking for is how likely is it that each potential result could occur. So in the case of coin flips, it's almost impossible for 100 coin flips to come up all heads, but there is a possibility. Does that possibility even come up once, in 10,000? Probably not. In this case, we could write, as I say, an equation for it. And in the coin flip case, we could say 1/2 to 100th power. And that's how because we can write that equation, we can identify the possibility of all 100 folks going heads. But in the example of it's going to snow tomorrow in Tucson, yeah, probably not. It's 94 degrees today, but if we ran all the simulations for tomorrow's weather in Tucson, and then even one of them claimed that it would snow tomorrow, then we have, a potential result that came from our data. We'd have to consider: is there an average, a mean, or a median, or confidence level value that can be worked? And here, confidence level, what I'm talking about is the same kind of 95 or 90% confidence level that we talk about with predictive analytics equations. But in this case, we're looking for the middle 95% or the middle 90% of the results of our simulations. And in this case, we remove the top, the bottom 2.5, top and bottom 2.5, or top and bottom 5%, to identify, okay, if you take away these outliers, then the likelihood that we're going to raise somewhere within this band of gifts remains. And I really like using confidence interval with Monte Carlo, mainly because it never fails that someone will see the outliers of an equation, a predictive analytics equation, and say, oh, well, there's a chance we might raise 3.5 million or whatever, even though the median is down to, like, 90% confidence interval between 500,000 and 1.5 million. Well, that 3.5 million outlier, it's better we just kind of ignore that, and say on, with the 90% of the time we're going to get some number between these two. So how do we actually run a simulation? And this is where Monte Carlo really kind of got to where it is. Monte Carlo is really the first foray into simulative analytics, in the sense of having something that was run on a computer. There's always, of course, been a possibility that one can simulate actions by doing the events. For example, you could take a coin and flip it 100 times, write down the result, flip it another 100 times, write down the result. Do that 10,000 times, and you have a simulation of flipping a coin. Most people don't have that kind of time, and I'd be bored to death doing that too. So really, it wasn't until the era of first computers in the 1940s that we could think about a machine-run simulation. And this man, Stanislaw Ulam, was kind of the creator of Monte Carlo. I actually hadn't seen a picture of him before I was looking for pictures for this presentation. I'm kind of struck how much he looks like Harry Lime, the third man. So Stanislaw Ulam was laid up sick in bed in 1946. He was a physicist at Los Alamos Nuclear Center in our neighboring state of New Mexico. And he and a number of other physicists were trying to figure out how many times a neutron contacted an atomic nucleus in a nuclear explosion. How far each neutron traveled before it contacted a nucleus, and how much potential energy resulted from those collisions. And Stanislaw realized that he had the measurements of previous explosions, so he knew how often a neutron would hit a nucleus in previous examples, and he knew how far a neutron would travel, and he knew how much energy. was created. But what he didn't know was what would happen the next time they tried to have a nuclear explosion, because this all seemed pretty random. And he couldn't come up with an equation that took into account all of the details of the neutrons' travel and energy. So while he was laid up, he was kind of thinking to himself what the probability of winning at Canfield Solitaire, which is set up like this. He was trying to figure out what the probability of winning it was. He thought to himself, well, I got some time here. I could do 100 runs of Canfield while I'm kind of laid up here. But then he thought to himself, well, computers are starting to get pretty good at simulating things like neutron travel, other problems they were facing. So why don't I try just to ask the computer to run Canfield 100 times? And then I could come up with the possibility that it would win. Now, I don't know if computers were really that powerful back in the 40s that they could have simulated Canfield, or even if they could, it would probably take them longer to simulate than actually play out the game. But in the process of thinking about it, he realized that what he needed to do to identify how much on average these neutrons traveled and their energy and how many times they contact the nucleus, if he could just simulate the number of previous explosions and simulate those explosions a large number of times, he could get an average of all of these measurements that he needed. And that would be a better way than trying to write an incredibly complex equation that might not take into account everything they need to take into account. So basically, he was simulating nuclear explosions with a computer and then writing down the results, tabulating those results, identifying what result was in the median, what the middle 90% were, all the things that we could do with Monte Carlo today. And as I say, he named it Monte Carlo after his uncle, who lost a lot of money there because he felt that the simulation of Canfield, which back then wasn't just a solitaire but also a gambling game, reminded him of that casino back in Monaco. So now I want to talk about a few basics of how simulative analytics works. And the first and most important is random number generation. All simulations are essentially based on the creation of random numbers. And random numbers really are created during this process to simulate the possibility of something happening. So say one single event, say, will a prospect attend an event, or will a prospect go to or give a gift this year? Say the single event has a 30% chance of happening. We could generate a random number between 1 and 100. And if the number is between 1 and 30, we can say that the event happened. And if it was larger than 30, it did not happen. So 30% of the time, we would be saying that the event happened, and the other 70% we would say it had not happened. And again, as long as the number is genuinely random between 1 and 100, we're going to get a good idea of how many times this event will happen if we run it 1,000 times. So this is a kind of block of, I actually put together this block for a previous example. This is a representation of running the feature RNG open parentheses, close parentheses, so the RAND formula in Excel. And RAND produces a number between 0 and 1. As you can see, these are all decimal points, 0 and 1. And here I was trying to simulate the number of times the coin flip would come up heads. And there I stipulated that, actually, yes, it came up heads, sorry. If it was between 0 and 0.5, then we would say it came up heads. And in this case, I've highlighted all the times that we got a number between 0 and 0.5. And in this case, we had 26 heads out of 40 throws. So we got more examples of coin coming up heads than we would have expected. This, in a sense, can be called statistical noise, but it also can give us a sense of, it is possible when we throw the coin 40 times that we will get 26 heads. So if we ran these throws over and over and over again, we should be getting closer and closer to the average of all those throws being 20 heads out of 40 throws. But this is an example that sometimes that statistical noise will show up when we have small numbers of iterations. And this is why we have the concept of iteration in simulative analysis. So let's start first with a list of items that have each of which have a defined percentage probability of occurring. So this is a gift officer's portfolio of 15 people for a certain project. This is their ask during the year, and this is the expected probability according to the gift officer that the prospect will make a gift this year of this amount. Now, first of all, if you recognize any of these names, I want to talk to you later about music, because these are some of the musicians in the obscure bands that I listen to. But the other thing I want to point out here is the probability table. If we try to feed this into any software package, including Excel, we're not going to get a result, because we have to express the probability as a number. In this case, I was given the probabilities low, medium, and high. And based on previous expectations and results of that development officer, I decided to mark low as 20%, medium as 50%, high as 90%. And that may change from development officer to development officer. It's worth looking into their previous history to see if they're overly optimistic about asks or not. In this case, I was able to identify. And as you can see, not many of these prospects had a high probability of giving. So even though it looks like there's a lot of money in these expected asks, when I ran the Monte Carlo, I realized that average income was not going to be large, because we just didn't have a lot of people who were going to give, had a high expectation that they would make the gift. And as I say, we no matter what program, we just have to change all of these figures to currency or numbers. So let's do one random number iteration using Excel, just because we've got Excel and everyone has Excel, and it's an easy thing to kind of look into how this works. I know Marianne is always kind of picking on me for using Excel, but I kind of like using Excel to figure out how a program or a problem works, because we can count the steps used and look at the steps used to identify how a more powerful program would calculate the event. So I have the same test file here, and in this first cell of iteration 1, I've typed the formula. If random number is greater than what's in cell C2, and in this case, I've put a $sign before C, so if we copy this field out here, it'll always stay in column C, because we're looking for the probability that Norman Blake will make a gift. So if the random number is less than 0.5%, then we will say, yes, he made the gift, which is in cell B2. And again, I froze the column for B. When we copy it out this way, we will stay on B for the expected ask. All I need to do for the first iteration is just copy the numbers down. And as you can see, the gift changed here because every time we change rand, we are recalculating this. So we're throwing a new random number into the cell. And in this case, the random number was higher than 0.5, so he did not make the gift in this iteration. All told, there are only a handful of people that did make a gift, and I can sum these up simply by doing a sum function in Excel. And in this case, we got the random number is going to reiterate every time I do something in this in Excel. So in this case, we ended up, once we got the random number changing, in this case, we got $172,000 for the year, which when you look at this ask amount, you would think, well, this person's asking for 100,000 from one person, 50,000 from 4 people, 25,000 from a couple of people. You'd think that's a lot of money that this person is asking for, but because the probabilities of each person making a gift were not very high, this person asked for 100,000, didn't make it. This person asked for 50,000, didn't make it. Actually, 3 of the people that gift officer did ask for 50,000 made the gift. So this might actually be a high number for an iteration. But that's really how we do one iteration of Monte Carlo. We identify the probability something will happen, and then the weight of that, if that event happens, the weight, in this case, the dollar amount that someone would make a gift. If we were doing this for event attendance, then we would have just 1, or in the case of a couple, 2, for the number of tickets bought, and then we would add them up the same way we added these ones. I should ask, are there any questions for now? I see Marianne said it worked for the Kentucky Derby this week. If it did work for the Kentucky Derby, congratulations, because I know the winner was an 80-to-1 outsider, and whoever bet on that was made a lot of money. I think if anyone has any questions, please put them in the chat so that I'll be able to read them out. So as I've said with the coin example, and the fact that we got a larger than expected number of heads on 40 throws, one iteration doesn't tell us a lot. One iteration, we have a lot of what's called statistical noise. And as Nate Silver's book title suggests to us, we're not looking for noise, we're looking for the signal that results from our analysis. And I had just like the dice example from, did I have a dice example? I kind of talked about traps, and then I realized I didn't have a real dice example. Also, instead, I'll say that we need a lot of iterations for any Monte Carlo analysis or simulative analysis to come up with a usable average. And when I say it a lot, I definitely mean a lot here. In my experience, we don't really come up with a usable average for Monte Carlo or usable table of results until we get to 10,000, 1,000 to 10,000 iterations. This depends, of course, on a number of factors. In my experience, the more events you have within each iteration. So this example I had only had 15 prospects, but if you're working with, say, an entire portfolio of hundreds of prospects, then you might be able to get away with 1,000. So, thanks, Carl. I missed your question, but I guess I answered it. So the other question we have here is, if we need to do for the entire population, do we need to ask the gift officers to put probably one by one? And as you say, yeah, yes, that is a lot of work. There are other ways we can determine the probability that someone might give a gift. For example, binary logistic regression, other forms of regression. So we can use other factors within giving history and what someone is, what someone has done in the past to identify potential giving for the next year. In occasion, I've just used, for example, for annual fund gifts, I've just looked into previous giving and tried to identify, someone made 5 gifts in a row, what their likelihood of making a gift the 6th year was, or if they had not made a gift in 10 years, what is the possibility they'll make a gift after 10 years? So really, the answer to that question is to use either a binary or logistic regression technique, or to look at previous giving behavior and attempt to identify based on that. I mean, especially for annual fund, you're just not going to be able to have a development officer be able to tell you how many what their percentage of each person in the database making a gift will be, because as you say, it could be 10,000 prospects. So that's something that you might need to figure out yourself with binary logistics, or if you've got if you've got a screening service or someone like Marianne helping you, then you can lean on them as well. Sabina asks, can you talk more about how you're assessing how accurate the gift officer's estimated success rate is? So in this case, this was a project I did many years ago. The project that I'm showing you is from a gift officer I thought had done quite well in assessing their previous asks. What I did really was, we had been fortunately doing this for a couple of years before I got to this institution. And so what I could do was do a survey of when that development officer said, I have a medium chance of making a gift, of getting this gift from this person. How often do they actually get that gift, or a high percentage? And I have to say, for some development officers, when they said they had a medium chance of getting a gift, they ended up having like a 15% chance, and then a low percentage is like a 2% chance. So really, I plugged in those numbers for every development officer. I just looked at their previous giving and I plugged them in based on their previous results, which, as you can imagine, didn't go down too well, because every gift officer likes to say, but this year is going to be different. We're really, I'm really going to get those gifts this year. And as you might imagine, there's also the fact that 2 years isn't really a lot of data to identify how good someone is at identifying their estimated success rate. And as you say, so, I mean, yes, part of the problem we have is that, yes, a development officer will concentrate on high, high probability prospects. But what I realized in studying previous examples of it was that's kind of baked into the probability percentage. You know, if someone says, I think this person is going to have a high chance of giving, that development officer already knows that they're going to focus on that person as a potential donor, and so that will affect. If they know they're going to be seeing prospect X 4 times or 5 times during the year they plan to, then they probably have a pretty good idea that they're going to have a higher probability of giving, and that's what they're going to tell me when they make the forecast. So in a way, it's kind of what I could probably say is a lot of times this is a self-fulfilling prophecy. If a development officer is going to focus on someone, then they're more likely to say that they're going to have a high probability of giving because they think they're going to close the gift this year, so they're going to focus on them more. But as you say, that could potentially affect the results, and this is why I think that having a Monte Carlo method and doing this does focus development officer activity on identifying how likely it is that someone's going to make a gift. And so getting that data will, the more data we have on this, I think the better it'll be. The Monte Carlo will be. I think it's like every predictive model. The more data you have to put into the predictive model, the better it is. So wrapping up here a little bit, as I mentioned, there are a lot of data analytics packages where you can identify, or you can use Monte Carlo method processing. IBM Modeler, I mentioned SPSS. One I didn't know about until I was doing the research for this is Power BI. As it happens, we're working on a Power BI project for a client. You can actually run Monte Carlo using the DAX library in Power Query. Minitab and MATLAB have their own Monte Carlo features. I would suspect that by now most statistical packages would include some form of Monte Carlo method. And if you want to kind of build your own simulation from the ground up, there are also ways of doing that. Python and R, which seems the most popular data analytics languages around these days, both have the capability of simulating a Monte Carlo method. Python, the packages you need are pandas and numpy. I don't know. I'm not a big Python person, so I will have to concede to the person who I was reading about that these are the packages you need. And are really using any random number package you like the most. One of the issues with random number generation is that technically random numbers are not random. A computer cannot identify a completely random number. They can only simulate random numbers by seeding their clock. And from what I understand, some random numbers are more random than others. So as I say, I'm not an expert in either of these languages. Simply by Googling Monte Carlo in Python, Monte Carlo in R, you can get some examples of how these are run in those languages. And I can show you a bit of his Monte Carlo in Excel. Now that we've run one iteration and it's sum, all we need to do is come up with more iterations. And in this case, we're just going to copy iteration 1 out to the right a bit. And I'm only doing 20 just for this example, just so we have an example. And to make sure none of these numbers change, I'm just going to copy and paste value. So now we have 20 examples of how this gift officer's year might go by. In this case, we can see this person, even though he has a 0.9 probability, he actually made a gift every year. So there's still going to be quite a lot of statistical noise here. The more iterations we have, the closer this person possible probability of making a gift will get to 90%. So our main focus now is these sums. These are the possibilities that someone would make. In this example, this person raised 162,000. Sometimes they didn't do so well. In this example, it's only 45,000. The best examples you can do this one at 312,000. So in order to do some analysis on this, first we're going to need to put these in a column and sort them. So we're going to use a nifty little feature of Excel called transpose. We're going to copy the totals, and then I'm going to paste special transpose. And what transpose does, it takes a column of horizontal numbers and makes them vertical, or vice versa. So in this case, we're going to hit transpose, and now we have the numbers as a column. And I can click on data sort, smallest to largest, and now we have these numbers sorted out as smallest to largest. So what we can do here is we've got a column of 20 numbers, and I'm going to just for our list, and our median would be the average of these two numbers, the 10th and 11th highest sums. So our median, it looks like it's going to be 143,500 raised. And again, when you look at these expected asks, I mean, the total of these expected asks is actually 418,000. So when you look at that, you think, if our goal is 400,000, surely, we're going to be close to that. But the reality, because the percentage possibility of making the gifts is not 100%, we're actually going to have a lower expected value. In this case, the expected value is 143,500. If we take the average of this, we can just do that by typing in average. And our average is pretty close to the median in this case. It's 146,325. One of the things you'll notice about Monte Carlo is we do not, especially if we have wildly different probabilities for each event, is that we will not have that same nice, neat bell curve that we have with binary logistic regression or other equations. Some numbers are more likely to come up than others. Also, if you have, say we're going to ask Rose Dougal here for 10 million instead of 10,000. Well, during the iterations when she does make a gift, this total suddenly jumps up from 162,000 to 10,062,000, which dwarfs any of the iterations where she doesn't make a gift. So in other words, that really skews her decision on whether to make a gift or not, would really skew the amount you expect from the year's donations. Oh, why do you choose if, first of all, yeah, why do you choose a random number less than C column in the prospecting gift? Okay, first, the reason is because, say we're doing this one and it's 0.2. If we say random number is larger than 0.2, then in the iteration, he'll make a gift 80% of the time rather than 0.2% than 20% of the time. The reason being that in Excel, the random number generated is between 0 and 1. And so 80% of the time, that random number is going to be larger than 0.2, but 20% of the time it's going to be exactly 0.2 or smaller. And that's why we do the random number is less than the C column. The other question, we could potentially do the opposite way, but then we'd have to do the probability that the person would not make a gift rather than would make a gift. Also, is there an easy way to do 1,000 iterations in Excel? The short answer is no. But the easy answer is really we can make, we can copy a column and then do Control-C, scroll all the way over to 1,000, column 1,000. And as I'm saying this, I'm realizing this isn't much faster than just doing iterations. And this is one of the drawbacks of using Excel, unfortunately. Excel is not optimized for things like this, but you can do it. I think that's when you don't have software, statistical software or other you don't have the programming techniques. Excel is a useful tool. I mean, I've used it for clients many times, and it does work very well, but it's slow, and it's hard to copy and then pull your data over 1,000 times. The one good thing is that if we title our column iteration 1 and then copy, like pulling the data over here, our column for the second iteration will automatically change to iteration 2, iteration 3. And so we'll know when we hit iteration 1,000. There is also one other trick to doing this, and that is to suppress calculations. So I use Excel all the time, and then never remember what things are. So in order to suppress calculations, you go to the formula tab on the ribbon, and go over to calculation options. Click manual for calculation. What manual does is it will not recalculate any of those random numbers when you click on anything. The result of that will be, first of all, these numbers aren't constantly calculated, but secondly, it saves a lot of processor speed. And so you will be able to pull all that data over to the 1,000s column and not have it try and recalculate every time you stop somewhere. So again, now we have this column, we've identified medium and mean. Now we can also calculate kind of a 90% confidence interval simply by saying, okay, we're going to remove the top 5% and the bottom 5% of results. In this case, because we only have 20 iterations, that 90% is just removes the first and 20th iteration, and we can say here that our 90% confidence interval is between 62,000 and 268,500. Now, unfortunately, this doesn't tell us a lot because we've only done 20 iterations. There's probably still a lot of statistical noise here that in these lowest end and highest end that we haven't gotten rid of And the only way to do that will be to keep doing more iterations, so that eventually we'll have something very close to what the average iteration would be. And as I say, in a case like this, because we have very few prospects or very few examples of the iteration within each iteration, I'd suggest 10,000 for this one. Oh, and you're welcome, Aaron. Thank you. Okay, it's now I was gonna say 7:55. I like the time zones here. I was confused, especially as we don't go back forward for daylight savings time here in Arizona. So I actually changed relative to everybody else this time. So it's but it is 4 minutes before the end of this presentation. Are there any more questions that anyone might have? And you can say them or put them in chat, by the way. If there are no further questions, let me thank everybody for coming. If you have later anything you want to ask me about, this is my email address, and I put my our Stefano website up. I always enjoy people asking about Monte Carlo. When I was going through my notes on this, I found that when I presented before, I had a lot of people email me later with very detailed questions. So if you want to do that, please go ahead. Oh, you're welcome, Adrian. Thank you. Once again, I just want to thank everyone for coming here. And again, if you have questions, don't hesitate to contact me. Unfortunately, I don't know what our next water cooler is on. Do you know, Ruthie?
I don't know off the top of my head, but give me a sec, I can find out.
Okay. And welcome. You're welcome to everyone. This is. You can probably guess just from the way I talk about this. This is something that I've found very interesting over the course of my work, and unfortunately, this is something that is. Although I've been working with this for 8 years, it's still something I have sometimes difficulty getting other people to realize its value. So anytime I have a chance to talk about it, I'm very appreciative that people have come to listen. Okay, so yes, Ruthie, it's a last minute prospecting on June 14th at 12 sometime is this presentation. And I'll just say I remember those days of doing last minute prospecting. So this is what I'm looking forward to seeing too. So thanks again. I'm going to stop the recording now, and I will hope to see everyone at next month's presentation. Thank you very much.